In the last video, we talked about properties and definitions for acids and bases. And the most important definition is the Bronsted-Lowry definition that says that acids are things that donate hydrogen ions, while bases are things that accept hydrogen ions. And we also pointed out that some acids are stronger than others, and some bases are stronger than other bases as well. So you have to memorize the list of strong acids, and those include hydrochloric acid, hydrobromic acid, hydroiodic acid. All three of those are halogens. Now you might notice that fluoride, or fluorine, which is also a halogen, isn't listed here. And the reason for that is because fluoride is so small that it doesn't dissociate because of Coulomb's law. The distance between the components are so small that it's hard to break apart. Then we have, over here, we have nitric acid, we have perchloric acid, and sulfuric acid. So those are strong acids. And the strong bases that you need to memorize are the alkali metals and the alkaline earth metals that are larger than magnesium. So the other alkaline metals would also be considered strong as bases when they're paired with hydroxide ions. However, we don't need to mention the other ones because they're not all that common. So lithium, sodium, and potassium, fairly common hydroxides, and they're all alkaline metals. Alkaline earth metals, again, bigger than magnesium. So calcium, strontium, and barium would be considered strong bases when they're paired with hydroxide ions as well. Again, the reason magnesium wouldn't count is that magnesium, again, would be very small and therefore very close to the oppositely charged particle and therefore difficult to separate. So when acids break apart, we say that they ionize. They break apart from being neutral, covalently bound atoms to ions. So it forms an ion. When we talk about bases, we say they dissociate because you have ions at the beginning and you have ions that are just separated at the end. So I just wanted to describe the difference in how we use those terms. Now, this is a general rule list, but really we can quantify how strong an acid or a base is based on their K value. We use Ka to represent the strength of acids and Kb to represent the strength of bases. So what K represents always is the concentration of products to reactants. And so if you have a large amount of products being formed relative to the amount of reactants you have, you're going to have a high K value, and that would represent a strong acid or a base. And for a small K value, where most of the material remains in the reactant form, then you would have a low K value and you would have a weak acid or base. So just to show you what that looks like, if you have a strong acid, you can see that the reaction shows a one-way arrow. You have all of it being dissociated, or ionized rather, into hydronium ion and its conjugate base, or whatever else is left after it loses the hydrogen. So you don't see any of the unionized form in there. When we're talking about weak acids, you can see that the majority of the molecules present, or the substances in here, are the unionized form of the acid. So you have a much higher concentration of reactant than product, and if you plug that into this value, you would get a low value for K. So low value for K means a weak acid. And the same deal for bases. If you have a strong base, it's going to completely form hydroxides, and then if you have a weak base, you're going to see that only some of it has formed hydroxides, and most of it remains in its basic form, undissociated form. Now, pause.